guys, and welcome to another calculus video. In this video, we are going to be solving this very awesome integral that was posted in my Discord by a viewer. So if you have an integral that you'd like me to solve, or a differential equation, or a topic you'd like me to cover at all, please feel free to join the Discord and leave it in there, or throw it down in the comments. So without any further ado, let's go ahead and jump right into this. So first of all, looking at this problem, there should be a few things that we notice. First of all, we have both cosine and cosh, which means that we're probably going to have to use the exponential form of these two functions right here, because that's the only way that they're really closely related. Next, we should notice that we have this x squared plus 4 on the bottom, which does not typically work well with trigonometric and exponential functions. However, the exception to this is when we're talking about trigonometric functions in the complex plane, because both of these functions work very well with contour integration. So maybe we should be trying to apply that. And so now what I'm going to go ahead and do here is, first of all, we're going to flip it, switch the bounds so that we're going from negative infinity to infinity. This is an even function, so that's perfectly okay. And then we're going to take the real part of e to the I sine of x, which is just going to be cosine of sine of x, if you go ahead and expand that out. And this is going to allow us to convert everything into complex exponentials, which are going to be really easy to use using contour integration. So we go ahead and substitute in the definition of cosh of x. So we divide by 2 and e to the cosine of x plus e to the negative cosine of x. When we expand it out, we're going to get two different complex exponentials here. E to the cosine of x plus I sine of x. Now notice that this is just e to the ix, and e to the negative cosine of x plus I sine of x. Now if we flip the signs here and we get cosine of x minus I sine of x, that's just e to the negative ix. So that's what we're going to have in the top here. So again, we still have to take that real part, and we're going to get 1/8 the real part of the integral from negative infinity to infinity of e to the ix plus e to the negative ix, which I know is a little bit of a mouthful, and it looks like a very, very complicated function, but again, contour integration is incredibly powerful, and it's going to allow us to very, very easily deal with these two functions. So we're actually going to split these up. This is going to become I1, the integral with e to the ix, and I2 is going to be the integral with e to the negative ix. So for the first one, we're going to consider the contour integral in the complex plane of e to the iz over z squared plus 4 dz. And we're going to be using the classic semicircular contour. So notice that we have a pole at z equals 2i, which is going to give us a residue. We also have a pole at z equals negative 2i, but that doesn't really apply to this contour. So our integral is going to take part of this. It's going to be this real axis integral, which is just going to be I1, and this outer semicircular integral, which we're going to call integral over gamma. And of course, this is all going to be equal to 2 pi I times the residue of the function at 2i. So first what we're going to do is we're going to say that z is going to be equal to x plus iy, where x is any real number, because again, we can go anywhere from left to right here, but y is going to have to be greater than or equal to 0. And this is going to help us bound our function so that we can evaluate this gamma contour. So this means that e to the iz is equal to e to the ix minus y. And then once we expand all of this out and then take the absolute value, this imaginary bit right here multiplied by e to the negative I is just going to disappear because we're taking the absolute value, or the modulus, of the complex number. So we just get e to the cosine of x times e to the negative y. Now we know that e to the negative y is between 0 and 1 because y is greater than or equal to 0. There should be a less than or equal to, but in this case it doesn't really matter, and you'll see why. So when we multiply this by cosine of x, it's just going to go from negative 1 to 1, and when we raise this all e to the power of this function, it's just going to go between 1 over e and e, which means that overall the absolute value, or modulus, of e to the iz is going to be less than or equal to e. Now this just allows us to use the ML inequality, or the estimation lemma. So if we find m is going to be equal to e to the iz over z squared plus 4, and then take the modulus of that for some z over the curve gamma. So we go ahead and bound this, and we find that this is going to be less than or equal to e over the modulus of z squared plus 4, again using what we just proved right here. And then using the triangle inequality, you guys can figure out that this is going to be less than or equal to e over r squared minus 4, where r is the radius of that large semicircle, and of course we're letting r tend to infinity. Something else to note here is that this only applies to values of z on the gamma curve, of course, because otherwise we wouldn't be using this r, right? This means that ml, we're just going to multiply this right here. that's going to be less than or equal to pi r times e over r squared minus 4, because pi r is the length of that large contour, and as r goes to infinity, this just becomes 0, so that means our gamma contour goes to 0, which means that our integral I1 is just equal to the residue at z equals 2I. So we go ahead and calculate this limit. It's not very difficult to calculate, so I'm going to go ahead and not really go over that, but we end up with pi over 2 times e to the 1 over e squared, and that's our value of I1. Now we're going to go ahead and calculate our second integral I2, and though there was a way that we could put this in the upper half plane, it's actually going to be a little bit easier to do this in the lower half plane. And the reason for this is our function e to the negative iz is going to be bounded in the lower half plane, but in the upper half plane, it's going to be unbounded. So this works out to our benefit. There is one thing though. We have to use this contour in the lower half plane, which goes across our real axis, which is going to be I2, and it goes along this gamma contour. But one thing that you should notice here is that this contour is clockwise oriented, meaning it goes in the clockwise direction. And that is incredibly important when it comes to using the residue theorem, because what this means is that we actually have to add a negative sign here in front of our residue, because usually the residue theorem gives us the value of an integral going in the counterclockwise direction, but this goes in the clockwise direction, so we have to keep that in mind. So we're going to do the same trick we did before in order to bound the function. Z is going to be x plus iy, where x is a real number and y is less than 0. And of course y is a real number as well. So e to the negative iz is going to be equal to e to the negative x plus y. And then doing the same thing as before, negative cosine of x minus I sine of, this says I sine of y, it should be I sine of x, sorry about that, e to the negative y. And then when we take the modulus, this imaginary part is going to disappear. So we just get e to the negative cosine of x times e to the y. And then again, since y is less than 0, e to the y is between 0 and 1, which means that negative cosine of x times e to the y is going to be between negative 1 and 1, and e to the negative cosine of x e to the y is going to be between 1 over e and e, or it's going to be less than e. So less than e, which means that e to the negative iz, when we take the modulus, is going to be less than or equal to e. So we do the same trick as before. We're calculating m, so it's going to be less than or equal to e over the modulus of z squared plus 4, or less than or equal to e over r squared minus 4. Same thing as before, pi re over r squared minus 4 equals 0, so our gamma contour goes to 0, which means that our integral I2 is just equal to negative the residue, 2 pi I times the residue at z equals negative 2I. So we go ahead and calculate that residue, again, very straightforward, and we get that the residue is equal to negative pi over 2 e to the negative 1 over e squared, once we multiply by 2 pi I, of course. Oh, I just realized I have another mistake down here. This should say negative 4 I. And so this is equal to negative I2, and so when we solve for I2, we get that I2 is equal to pi over 2 times e to the negative 1 over e squared. So overall, our integral I was equal to 1/8, the real part of I1 plus I2, and they're both completely real, so we don't need to worry about that. So it's going to be pi over 8 times e to the 1 over e squared plus e to the negative 1 over e squared all over 2. And this is just the definition of hyperbolic cosine, so we can write that this is going to be pi over 8 cosh of 1 over e squared, which I think was a very beautiful result. I think this was a relatively easy problem in the grand scope of problems that I usually do on this channel. But I hope that you guys were able to solve it by yourself, or at least give it a try, or at least you enjoyed watching the solution. So look out next week. I should hopefully have some more videos coming out teaching integration methods if you guys want to watch those. And yeah, hope you guys liked the video and you learned something, and I'll see you next time.